right, everybody, welcome on in. Welcome back. So I saw, in fact, this class I forgot to check this morning. Let me do this off screen so I don't show any private information of any students, but let me just double check some real quick here. So we're looking at, okay, so we got 24 people signed up for the homework. That's good. That's almost everybody. I think we have, that leaves us just a handful of people still left to do that. So that's great. Great start, everybody. You got in there. You got signed up for the homework. That's really good. Right. So a couple things to get out of the way to make sure everyone knows what they need to do here. Let me go back to the course and I can put that back up here. Okay, so looking at things, so hopefully, I know many of you have started the quiz and the getting to know each other discussion, right? So there's posts here, so that's great. If some of you want to start your study group, stuff like that, that's great. So just be aware, you have 2 of these Canvas assignments are due today in that introductory module. So I haven't had a chance to look and see how many people have completed them yet. I usually look once they're due, because then once no one's working on them, then I can sort of make sure those grades are all finalized and like the discussions, I'll go through and grade those. There's no point in me doing it before people are still writing stuff. But notice those are due today, June 22nd. So make sure if you haven't done that yet, that you remember to do that by the end of the day, because those are, relatively easy points. Hopefully you'll get some kind of at least an 80% or, hopefully a 90 or close to 100% on this quiz. All you have to do is know what's in these top, the syllabus and the class meetings and homeworks and exams and testing center, read that stuff, understand how it works, answer the question in the quiz. That's some easy points, relatively easy. You got to do a little bit of reading. And then the getting to know each other, you just make a discussion post, respond to people, see if you want to form a study group with some people. Again, you don't have to do anything that makes you uncomfortable or share a phone number or anything that you don't want to do, but it can be very, very helpful to have a support group in this class so that when you're confused, you have some people that you can text or say, hey, that test is coming up. You want to get together and go over the study guide or, whatever, so that you can do that. So that's up to you how you want to do that, but make sure those grades are due today. So make sure that you get those done if you haven't done them yet. And then so what else have we got going on? So we've got the homework. Remember, we've got this calendar here. So I kind of I give people a little bit of leeway because I know the first week is always weird. So the first set of homework is due Monday, which, as you can see, if you look at the whole schedule, is not normal. Normally, homework will be due either in the middle. Windows always does that. If you put it in the wrong spot, it expands it to everything. You can see usually they're going to be later in the week, but I know this first week, especially since Monday was the holiday, Juneteenth, and then Tuesday we actually got started. It takes people a little while, so first homework's due on the 26th. That's a batch of homework, so don't wait till the end and then try to get it all done, because that's 7 things you're going to be working through. That's too much. That's a lot. So hopefully you've already started that, or you're going to start it tonight. Even if you start it tonight, it's going to keep you pretty busy. And then notice just a few days later, your next chapter stuff is due, and that's another 5 units. So, that's just how it goes in the summer. We move fast. So if you're waiting until, close to the due date to start the homework, you're going to have a really hard time this summer. The goal is to outrun it, right? Try to stay ahead of it, like it's a bear chasing you or something. Stay far enough ahead that those due dates are not going to catch you, right? You're going to stay ahead of them. It's way less stressful. You'll understand the material better. So just pay attention to those due dates and stay ahead of them. Try to outrun them. And then you'll should stay on track to finish the course successfully. So just be aware of that. We're going to go over some of Chapter 1 today, especially the trickier parts that students struggle with. So we'll start that in a little bit. I do want to remind everyone there's these first two sections you should look at to understand the ebook and the answer entry guide. There's, there's gonna be times where you might get confused about how to enter your answers, and it's always helpful to be able to, put your answers into the computer in a certain way. So just let's remember, if you go to 1.3, I'm gonna look at the teacher preview. Let's see if I move this over a little here. Let's see. So I just want to point out, remember there's these videos and then sometimes links to the ebook. So don't forget those when you're working on a particular problem. So if there's something we didn't have time to go over in class, or you didn't catch it in one of the, maybe you didn't watch or whatever, you missed it throughout the videos that you're supposed to be watching, you can always just watch the video that pertains to that exact problem. So it sort of helps you kind of get some very specific help. You're going to want to pay attention to like how you draw lines on these. So if you click here, kind of play with this a little bit and make sure you understand how the lines work, like how this, how you create these lines here and how those go, so that you can, that's not a very good one. That's clear all. But anyways, so you're going to, that's going to seem weird at first. So you're going to want to play around with that. And that's part of, I believe they show you when you do that, whatever they called it, the answer entry guide or whatever it was. Also, there's a few shortcuts that you notice when you click here. It opens up a box where you can click things. Say you want to do a square. So I could put it in X, and then I hit this box, and it gives me the exponent there. So I can make that X squared. So you can click the box. That's one way to do it. Also, if you watch, I'll do it without clicking. So I'm in there, but notice I'm not going to use my cursor's above here. I'm not going to use it. There's usually shortcuts for this stuff. So you'll find like people who know programming and stuff like that, a lot of times they don't want to, if you grab the mouse and you're clicking things, it just takes forever. If you just type stuff out, it's usually much faster. So like if you want to do an exponent, it's the caret. That's the number 6 on your keyboard. See, there's that little symbol above the 6, above the T and the Y on the keyboard. So if you do Shift 6, you get what's called the caret. That's typically exponents. So you could do X, Shift 6 gives you the exponent, and then if I hit 2, now I've got my X squared. So almost everything in here is going to have a shortcut that you can do by typing. It's just a matter if you care or not. So it's up to you. You can click buttons if you're a button clicker. You can type if you're someone who likes to be a little bit more advanced with your computer usage. It doesn't really matter. It's just your personal preference. Let's see here. We've got okay, we have 2 comments here. Let me get into these. So what do we have? Does the Chapter 1 review help give a gauge on the concepts that will be featured in the first exam? So the first exam covers, I think, roughly the first 2.5 chapters. And the answer is yes. There's some very important topics. A lot of what we're going to spend time on today is called limits. And those are very important for all of calculus. And there will be limits on the first exam. But then in Chapter 2, there will be new material that will also end up on the exam. And then like the first half of Chapter 3, that will also be on the exam. So it's hard to say because it's a good question. Calculus kind of comes in chunks. Like there's kind of 3 major topics we're going to look at, and they're all very deep. So they all have a lot going on in them. But calculus essentially is divided into 2 major pieces. You've got your derivative calculus and you've got your integral calculus. But before we get to those, we'll be looking at a thing today called the limit. And you have to understand limits before you can understand derivatives or integrals. So if you don't understand limits, the Chapter 1 stuff, the whole rest of the class isn't going to make any sense. So limits will be a topic on the test, but then we get into, in Chapter 2, we get into derivatives and all sorts of different topics on derivatives. And then the last couple chapters of the class are on integrals, and that's, like a whole different topic. So to answer your question, like Chapter 1 will give you some bearing, some gauge as to the first exam, but it's not complete. It's not the whole thing. And there are some people who struggle with limits that do better with derivatives, and there's some people that do it the other way around. They're great with limits, but they struggle with derivatives. Actually, most people that get limits are pretty good with derivatives if you really understand them. Some people think they understand them, and they don't. But if you really understand them, you probably find derivatives not too bad. I hope that answered your question, Elizabeth. And then we have for tutoring, I tried joining the online meeting more than once. Is there a link we are supposed to use? There's just the just that one I think I showed in class where it's through the Ventura College webpage. So if you go to the Ventura College webpage and in the search you just put tutoring center, it should come up. That should be the link. There's like directions in there on how to do it. So if that's not working, then okay. Well, I would say try again. Sometimes, I don't know, maybe a tutor had to go to lunch or sometimes people have to cancel. So I'm not sure. I would try it again, maybe at some different times or see if you can go in person. That's always helpful as well. So yeah, sorry if that link isn't working, but I would try something else because it should be working. It should work if they say it is. Let's see. So if I go tutoring center, online tutoring. Yeah, that Zoom link should work. You could give them a call in the tutoring center. There's a phone number on there. You could give them a call and see if maybe I don't know. You could call them and ask if things aren't working properly. They should answer the phone if you're calling during business hours. So you could give that a try, but it should work. Our tutoring center is pretty good in general. Okay, other questions or concerns with things? We're doing good? Okay, those are great questions that we're getting asked. Glad we could talk about that stuff. Okay, so like I said, make sure you're through the introductory chapter. There's a little bit of review. You can skip that if you want and then dive right into chapter 1. In fact, the first half of chapter 1, and just as a reminder, so remember, if you're in Zoom, you're only going to see a green screen behind me. If you're on the YouTube stream, then you'll actually see what I'm talking about, Canvas and the mathematics and stuff like that, which is going to be pretty important for today. The first half of chapter 1 should be review. It should be stuff that you've seen at some point in the past. It may have been a long time ago, or maybe you didn't, but those should come back pretty quick. How to use functions, what is composition of functions, linear functions and slope are actually hugely important. People underestimate lines and slopes and go, well, that's what we learned back in like beginning algebra. That was years ago. But you'd be surprised how much the study of calculus relies on finding equations of lines. You'll see that later today when we talk about this thing called a tangent line. We'll be talking about secant lines. So they actually are hugely important, and you want to be able to find the equation of a line. It's literally like one of the tests you generally see on a test, which is find the tangent line to this function at this point, and it comes down to finding the equation of a line. So you want to make sure you're comfortable with that. And then we have the big topic for this chapter, which is limits. Continuity is an important topic in calculus, but really limits is like major. It's a huge topic. And notice if I click it, you can see there's a lot of video here. There's me with an introductory video that I made, and then there's these 2 full Professor Leonard videos where he just goes through examples in like excruciating detail. Now notice that I put a point in here. After a certain point on the second video, you can stop because he goes into trigonometry, and we don't do calculus of trigonometry in this class, so you can ignore that when he starts talking about sines and cosines and tangents. You don't need that. But before that, it's a really good introduction to how this stuff works, and it's because limits are hugely important. So I want to sort of get a little bit philosophical here for a second, because I think a lot of people it's unfortunate the way we teach math in this country is not great, and also the way that people learn math in this country is not really great. So there are problems with math education. Many people are trained as they move through their K-12 education. They become trained that math is about memorizing how to do problems, and it is not. That is why people hate it. That is why they don't actually learn it very well. And unfortunately, oftentimes classes are taught from a perspective where we encourage students to memorize problems, or we reward students for memorizing problems. And the reality is, the world we live in today, that's just not important. Memorization is not really that important anymore, because the reality is, in the real world, if you ever forget a formula or something like that, all you got to do is you just Google it, and boom, now you got your formula, right? You forget the formula for a derivative, just Google it, and there you have it, right? So is it really useful for you as a human being to memorize a bunch of things? Not so much, right? And even memorizing how to do problems, like, it's important that you can do calculus problems, but really what's important is that you understand calculus. That is way more important. The reality is, many of you, if you actually get a job where you have to use this kind of mathematics, you probably are also going to have a piece of software at your work that'll do a lot of the calculus for you. So having memorized problems doesn't mean anything if you don't understand the calculus. What you have to be able to do is know how to use the calculus. When your boss comes to you and says, you need to figure out what price we're going to price this new product at, and you have to use a bunch of calculus to do that, and you go, well, I don't know. I could find the derivative using the power rule, but I don't really know how to do what you're asking me. Then what's the point, right? That was a totally useless endeavor for you to try to get through that business calculus class. So what's important is that you know how to use these tools. It's important that you can do them, but keep in mind, it's really important that you know how these things work. Can you actually implement these things in a way that are meaningful? And I'll tell you, many of you have different majors, but I've found myself in classes, and I have students that take these certain classes. The students that can actually use the business calculus in those classes kind of rise to the top. A lot of times, like, when they have to actually use those tools, many people in the class that didn't really learn the business calculus very well kind of look around at each other and figure out who they're going to get help from. But those people that actually learned how to do that stuff correctly, those people are now in high demand, right? And you can imagine, if you're high demand in the classes, you're going to be high demand in the workforce, because, here's a person who actually knows how to do valuable things for our company, right? So keep that in mind. Don't focus on memorizing problems. I mean, you have to know how to do the problems. But again, you want to think big picture. Do I actually understand how to use this stuff? And if the answer is no, then what's the point of any of it, right? It's not really going to help you down the road, and you're not really going to stand out in job interviews and against other people and stuff like that. So just try to, get the concepts as well as the mechanics, being able to do the problems. Okay. All right. So with that said, let's jump into limits. You can look at some review for linear functions and stuff like that if you need to go through and do that. I've got some videos here. These are my older videos. They're a little bit different style, but you can kind of remember how to find slopes. Here's a couple chemistry tutor videos, which are math videos, but I want to really focus on limits because, like I said, the definition of the derivative, which is chapter 2 and 3, those involve limits. The definition of the integral, which is the second half of calculus, those involve limits. So you really have to understand what that limit is. And a lot of people really struggle with limits. And I think part of that is because with limits, it's way too complex an issue to just memorize. Remember how we talked about that? I just was talking about that. Many of you go to class, I do 5 examples, you go home and do 40 examples, then you've memorized how to do that problem. Well, limits are very complex, and there's very many different types of limits. So if you understand conceptually what a limit is, you'll see people, maybe not in this class because we're online, but if you're in the classroom, you'll see, I put a limit problem on the board. Many people are struggling with it, and other people just look at it and go, oh, here's the answer. And you're like, how did you get that instantly? And it's because they actually understand what the limit is, right? So let's jump into that. Let's see, where did I want to start? Okay, before we get too deep into, well, let's see, actually, yeah, let's do this first before we get too deep into limits. So you may or may not have seen there's this thing called the difference quotient, and the difference quotient is this thing in blue right here. Is this bolded? Let's make this bold. Okay, the difference quotient is this right here, f of x plus h minus f of x over h. I'll do a difference quotient problem here in a little bit, but you will be doing those as part of your homework. But again, it's one of those things where it's like, okay, I can do a difference quotient, but do you really know what it means? Do you really understand it? So you can see we've got a red version up here, and this hopefully looks familiar to you. This red version up here, you might be thinking like, oh, isn't that slope? Yep, this is the slope of this line. And you probably at some point saw someone give you, there was a drawing. Every algebra book has this drawing in it at some point. Most of your teachers probably drew this in algebra class. If we want to know the slope of this slanted line segment right here, it's y2 minus y1 over x2 minus x1, and we use m as the symbol for slope. So that's just slope of a line. The part that's in red, you understood this back in beginning algebra, right? Your algebra 1 class, you saw this, okay? So what it is it's the ratio of the rise to the run. So it's the vertical divided by the horizontal change. That gives you the slope, right? That makes sense. If you go on a hike and that hike has an elevation gain of 1 foot for every 100 feet that you walk forward, that's a pretty low elevation gain. If you have an elevation gain that goes up 6 inches for every foot that you walk forward, that's a steep elevation gain, right? So you're comparing the vertical gain to the horizontal gain. That's all slope really is. And slope in general we think of as the rate of change. Okay, you're going to see a few types of rate of change in this chapter, but I checked the videos that are in the problems do a really good job describing it. So if you still feel a little unsure after these videos, the videos that are attached to the homework problems do a good job describing it. Okay, so the red part hopefully looks familiar. That's how you derive the formula y2 minus y1 over x2 minus x1. It's the ratio of the horizontal and vertical distances. Okay, down here, it looks pretty similar, right? We're seeing the same shape because in calculus, what we do is we very frequently deal with the rate of change, the slope. We have different ways of dealing with slope. But we don't like to use that same labeling that we used in algebra. The y2 minus y1 over x2 minus x1, that's not the standard way of approaching slope in calculus. What we do is we like to do things in calculus from a functional perspective, right? That's sort of the modern approach to calculus, is that most of things are functions when they can be. Some things aren't going to be functions and you still have to deal with those, and those will come up a little bit when we do implicit differentiation and stuff like that. But we try to do things from a functional standpoint. So this picture right here really is just like the picture in red. The blue one is just like the one in red, but it's labeled differently. So like here, the way we find in the red picture the horizontal distance, we call that x2 minus x1. Well, down here, we just call that distance h. Why? Because it's convenient for the way we do calculus. In calculus, we do different things with slope than you did in algebra. So, if we're using a tool in a different way, sometimes you have to change things a little bit. Now, remember, this throws people off a little bit. In calculus, most things are done from a functional perspective. So when you see things like f of x and f of x plus h, remember, those are just y values, right? F of 2 means the y value that you get when you plug the x value of 2 into the function. That's what that means. So whenever you see stuff like this, I know a lot of times students, their eyes kind of glaze over because it's a lot of notation. And I know that's one of the tricky parts of math is learning the notation for a thing. And it kind of just looks like alien writing or something. But you really are going to have to digest that stuff in a calculus class in order to really understand it. So keep in mind, function values are just y values. Well, that kind of makes sense because up here, the y values are in the numerator. Well, down here in this numerator, those are just y values, right? Down here, this distance in the denominator, that's the distance between our x's. Well, down here, that's what we labeled h. So our h is still the difference between our x values. It's just we're not calling them x values anymore. We're just calling that distance h. So what does this really mean? Well, we have a point here where we take an x value, and to get the y value, we plug x into a function f. Whatever the function is for this line, that's our function for this problem. And then if we go h, well, if this was x, then when we go h over, we're now at x plus h, right? So that's why this x value is x plus h, and the corresponding y value is f of x plus h. So it's just this, except instead of calling it x's and y's, we're calling it x's and f of x's. That's the only difference, and we're using the distance of h in there. So when you see this we call this the difference quotient. When you see that coming up, don't let it intimidate you. Some of the problems get a little bit complicated, I admit. We'll go through one in a little bit. But at the end of the day, that difference quotient, it's just the slope. It's just slope. So just kind of don't let yourself get nervous or upset. Just go, I did slope back in algebra. This will be fine. I can work my way through this. Okay? So don't let it intimidate you too much. Let's do a problem like that. See if I can get this. Over here. So let's do a difference quotient problem. Oh, and I'll take roll in a little bit. Find the difference quotient for f of x equals x squared minus 2x plus 1. Okay, find the difference quotient for f of x equals x squared minus 2x plus 1. So this is an example of a type of homework problem that you'll have to do. So we don't 100% know what this means yet, but we're going to get that a little bit in class, and then also when you watch those videos that are inside of Canvas, you'll get the sense of it. So let's see. Let's first write our difference quotient. Okay, so our difference quotient is f of x plus h minus f of x over h. Okay, so our goal is to fill in the pieces here and then simplify things. So f of x is easy to figure out because that was given to us in the problem. So that's going to be easy to plug in. It's going to get plugged in right here. Now, the thing is you have to be careful of when you're plugging f of x in is see this negative in front? That negative applies to the whole polynomial. So make sure, like really what you should do, you'll see me do this, is I'll write minus, and then I'll put the f of x part in parentheses, and that's going to remind me to distribute that negative to each piece. I'll show you when we get to that. The trickiest, in my opinion, the trickiest part of this problem is figuring out what f of x plus h is. And it's not too bad, you just have to be careful with your algebra. So let's see. If we go f of x plus h. Okay, so what does f of x plus h mean? That's what we get when we plug x plus h into our function for x. So remember, whatever's in the parentheses, that means replace your variable with this in the original function. So this is our function f. f of x plus h means turn these x's here into x plus h's. So for us, that's going to look like x plus h squared minus 2 x plus h plus 1. So all I'm doing right now is just figuring out that f of x plus h piece. Okay, so see how I've taken this and everywhere there was an x, I replaced it with an x plus h. So that's why we got x plus h squared minus 2 times x plus h plus 1. Okay, now what we have to do is simplify this down. Now what you don't want to do, this is very common, even people who were good at algebra, when they get into calculus, for some reason people start making this mistake. X plus h squared is not x squared plus h squared. Do not write this as x squared plus h squared. What you have to do is multiply x plus h times x plus h and FOIL that out. So let me show you. Okay, so what do we have here? Well, x plus h squared, anytime you square something, it means that thing times itself. So x plus h times x plus h. Some of you are kind of seeing, oh, it looks like we're going to FOIL that in a minute. That's exactly right. That's what we're going to do. Notice here I've distributed the negative 2 in, giving us negative 2x minus 2h. And then this plus 1 hanging out on the end just stays plus 1. Okay. Now we're going to multiply this. We're going to FOIL this piece out. Let's do that. So that's going to give us x squared plus 2xh plus h squared minus 2x minus 2h plus 1. And then just in case you're kind of forgetting how this works, you FOIL this. So the first gives us the x squared. So FOIL is first, outer, inner, last. So our outer gives us an xh. But notice our inner gives us an xh too. So we got an xh from the outer. We got an xh from the inner. That's 2 xh's. That becomes 2xh. And then the L part of our FOIL, the last, is h times h is h squared. So that's where x squared plus 2xh plus h squared comes from. Then we've got our negative 2x minus h that we had from the previous step. And then our plus 1 is just kind of tagging along at the end. So what we've done is we've figured out, I guess I should really have equal signs here. What we've done is we've figured out this first part, the f of x plus h part of our difference quotient. Okay, so let's take this and copy it. And what we're going to do is fill in our difference quotient with the pieces that we know. I wonder if I'm going to have enough room here. I'm going to give it a try. I might run out of room, but let's see if we can make this work. Okay, so we know we have an h on the bottom. Okay, so the tricky part is the top. So this f of x plus h here, we just figured out what that is. It's this, right? This is our f of x plus h. So I'm going to write that in there. This becomes this piece, and then it's minus f of x. We want to put that whole f of x in parentheses. Let's see if it's going to fit. Well, I've got some error here. Let's see. There we go. I had hit the same button twice, so it got confused. Okay, so this is what the difference quotient looks like when we plug everything in. So this first part, that's our f of x plus h. That's what we figured out right here. And then this minus f of x piece, we've got our minus, and then this is f of x, so I plug it in here. Notice those, you can see what I was talking about now with those parentheses and the negative. Without the parentheses, the negative would just apply to the x squared, but we want it to apply to every term in here. So those parentheses make sure we're going to distribute it in, and then the denominator is just h. Okay, so our next step is to distribute that negative that we were talking about. So let me grab this. And then I'm just going to take out the first part here. And then we're going to distribute that negative in, making this a negative, and then this one a plus, and then this one a negative. Oh, in case you're wondering what's going on, it's really hard to type math live. Like, especially if you've ever tried to do math in Word, it's just crazy. It takes forever. So basically, this is a software that gets used in mathematics. We use it to type. It's basically typesetting. It's kind of part programming or scripting, part typesetting. And it typesets the math for us. So it allows me to write math relatively quickly in a way that is we can see it well. So basically what happened, the signs changed in front of my x squared, my 2x, and my 1, right? Notice how the signs are different because we distributed the negative in there, okay? So now, I know you're right at the point where you're like, this is looking ridiculous, right? This is looking super complicated. But there's good news. We're right at the point where everything is about to simplify. If you've gotten to this step in your problem correctly, then a bunch of stuff is about to cancel out. And it actually gets really nice. So here's how you look at this. Every term that's in that last piece, that f of x on the end, should cancel with something that came earlier. So do you notice here we have a negative x squared, and in the beginning of the problem we have a positive x squared? Those cancel. Notice how we have a plus 2x, and then right here we have a minus 2x? Those cancel. Right here we have a minus 1, and guess what we got right here? A plus 1? Those cancel. So if we go through and take all those terms out, it's going to look like the following. Let's see, that 1's gone, the 2x is gone, and the x squared is gone. Let's see if I got everything right there. Nope, I got one. Yep, there we go. That's right. So the x squareds are gone, the 2x's are gone, and the 1's are gone. That should happen. If every term from your f of x doesn't cancel out, go back. It means you made a sign error or something like that. Okay, but see how simple that got all of a sudden? And now what you're going to do is look at this and say, well, can't we divide the top and bottom by h? And the answer is yes. What some people do is they try to just cross out these h's on the end, but you want to remember the difference between canceling and crossing things out. A lot of students treat canceling as wishful thinking. I don't want these things to be here, so I'm going to draw lines through them and call that canceling. That's not canceling. Canceling is a division. You are dividing the top and the bottom by the same thing. If we divide the top and bottom of this by h, then we lose an h in the entire numerator. Okay, not just the one on the end, the entire numerator. And when we do that, we end up with 2x plus h minus 2. Oops. And we will see right there, that is our difference quotient. Okay, so it takes a little bit of work, but once you've done like 5 or 6 of these problems, it kind of becomes natural because it's kind of the same thing every single time. So it takes a little work to get the hang of it, but that's how those difference quotient problems work. And I believe I have another one in here, somewhere in here. There's a difference quotient problem. Somewhere there's a video in here on difference quotient. So, but also I just did one. So you got it there as well. Where am I? Right? So there's your difference quotient. Any questions on how any of that worked? Okay, then let's move ahead, start looking at what some of this stuff means. So we talked about this. Now we have this thing called secant lines and tangent lines. Secant lines and tangent lines in calculus are very, very important. You're going to start seeing, when you do the homework, you're going to start seeing the terms average rate of change and instantaneous rate of change. And those are really important. In fact, you know what? 40 minutes in, I'm going to take roll before I forget, just to make sure that we have roll accounted for. So I'm first going to look in Zoom and see who I can get here. Okay, so this is 622. Who do we got? Okay. Okay, if you're on the YouTube stream, can you quickly just put your first name followed by the last letter of your last name? So like for me, it'd be Topher F. That way you don't have to put your whole name if you don't want to. But then I can figure out who's here and who's not. Okay, Ashley V. Thanks, you guys are doing great. Trey B. Kyle M. All right, David F. I don't have you on my roll, but I think if I remember right, you added probably after I printed this roll. So I think that's okay. So I'll write you in here. So I think that's what's going on. Okay. I hate taking all this time, but we have to do it. Part of the reason the school's so strict about attendance is part of it has to do with funding, the way the state funds us. Most of the funding for colleges doesn't come from tuition. It comes from taxes, basically. The state gives us money. And so there's this calculation, and so we have to make sure our rolls are tight because it's part of how the state calculates funding, and they don't want us having people in the class and getting funding for people who aren't actually showing. So plus sometimes we've been seeing more where if there's challenges to things, like where a student has a complaint or something about a teacher, sometimes if they have solid roles, it fixes the problem a little bit easier. So we're all being encouraged to keep really, really good roles. I hate that it takes 5 minutes or whatever to do it, but thanks for your patience. So, and I did have to drop a couple people. That's part of what census is. We have to drop people who haven't shown up right at the beginning of class. So I already had to drop a few people for that. Let's see. So it looks like I just want to make sure that I don't drop anyone I don't have to. Okay, so it looks like people are good, except for did I miss Jennifer D? Jennifer D, if you're in here somewhere, make sure you get my attention so I can mark you as here, because otherwise I might have to drop someone else here. Okay, so Jennifer D, get my attention if you're here. Otherwise, let's see. So there's a question. It looks like maybe it got figured out about the dividing. Yeah, we're dividing by h in each term in the numerator, effectively removing an h from each term. Yeah, we're dividing the entire numerator and entire denominator by h. That's right. Right. So, and let's see there. So there was a question, 2h divided by h equals 2. Yeah, so if we've got 2h, if you divide out an h, it would be, what was that problem like? It was, we had just end up with a minus 2 on the end there. Negative 2h divided by h gives us a minus 2, right? Okay. Was that the question? Or if there's other questions, feel free to jump in there and ask, because this is a thing you're going to have to do, is that difference quotient. Okay, good. We're good. Okay, so with that said, secant lines and tangent lines. So you may or may not remember, if you take a line that goes through 2 points, we call that the slope, right? So say we've got a curve here. We've got this black curve, and maybe that curve represents some quantity that we are interested in. Maybe it's distance or speed or something like that. So the black curve is the thing we're trying to study. Maybe it's distance. Let's talk about its distance, right? Well, we can take 2 points that are on that curve and figure out the line that goes between them. And this line, the orange line, represents the average rate of change, where the black line represents the actual rate of change, but it represents the actual values that we're concerned about. I should be careful how I say that. This orange line represents an averaging, but lines are easier to deal with than curves, right? I mean, imagine some complicated polynomial that someone asks you to analyze, or imagine someone gives you a line and asks you to analyze it. And that's effectively like a major chunk of what we do in calculus, is we take really complicated curves and we approximate them with a line, and then we use that line to give us information about the curve itself. Okay, it sort of is a way of simplifying something in a very short period. And it seems like that seems kind of counterintuitive. How could a line capture that same behavior? Well, that's a lot of the concept of calculus, is making sense of that and understanding how does that work. So imagine that this black line, let's turn off the purple one for a minute. Imagine that black line is your distance, right? You're on the freeway and you're driving, and at certain time periods, you're keeping track of how much distance you have covered. Well, if we take track of it right here, let's do this. Right here at this point, we make a little marker in our notebook and say, oh, at 1 hour, here's how much distance we traveled. And then let's put the dot here, at 2 hours, we make another note in our notebook about how much distance we covered. Well, if we look at the distance that we covered between hour 1 and hour 2, and we divide by 1 hour, then that will give us the average speed that we traveled over that hour, right? That's the average speed over that hour. So the slope in this case, you can see the example, the slope of this line is the average rate of change for our speed from hour 1 to hour 2, which is great, except if you think about it, if you know the average speed that someone traveled over an hour, do you really know anything about how much they were traveling at any given time? I mean, not really. Like if you go from here to, whatever, Chatsworth or something in an hour, someone doesn't really know, well, where were you slowed down on the freeway and going 5 miles an hour? Where was it wide open and you were going 75 miles an hour? Where did you have to pick up and slow down? There's no way of knowing that if all we know is the distance we covered over an hour and that it took an hour to do that. But what if we shrink that time down? What if we do 10 minutes instead of an hour? Well, now it's probably going to be a little bit more accurate because it's a smaller time period. There's less time to have those, slowdowns, and it opens up again and all that kind of stuff. So if we took the same thing, we looked at our rate of change over 10 minutes instead of 60 minutes, see how that line better approximates the curve? Like out here, it's not approximating the curve very well. But as we shrink that time period in between our observations, the orange line is doing a better job approximating the black curve. This is a huge, pivotal concept in calculus. As I bring these 2 points closer together, the orange curve is acting more, or the orange line is acting more like the black curve, right? So here at 10 minutes, approximately, we'll just say that's about 10 minutes, it's a little more accurate, right? And what if we did 1 minute? What if we marked our distance at 1 minute or at 1 hour, and then we marked it at 1 hour and 1 minute? Well, that's an even shorter time period, so it's more likely to give us an idea of what we were traveling at any given time. What if we shrunk it down to a second? We tracked our distance. 1 second later, we track our distance again. Well, that's not a whole lot of time to speed up and slow down. So if you look at your average speed over 1 second, it's probably pretty close to what you were actually doing, right? Unless you happen to be slamming on the brakes in that 1 second or something. What if we did 100th of a second or 1,000th of a second or 1,000,000th of a second? As that average rate of change shrinks down in time period, it becomes closer and closer to the actual speed you were going. And that's this idea. As we take the average rate of change and we shrink the time period down towards 0, we approach what's called the instantaneous speed, and that's given by this line, this purple line, which is called a tangent line. So a secant line is a line that goes through 2 points on your curve. The tangent line, let me get this orange one out of the way. This purple line, notice how it comes in and it just touches the line right at the 1 point we care about and keeps going. It doesn't cross it the way this orange one does, right? It just comes in and touches it. That's called tangent. When something comes in and just barely touches a shape and then keeps going, it doesn't cross through it, like it's not cutting through it. So the purple one is called tangent. The orange one is called secant. And as the time period, or the h, remember the h was the distance between our x values of our 2 points? As that h shrinks down, our secant line approximates our tangent line. You can see it. It basically becomes the tangent line, right? And that's what we do in calculus. The difference quotient gives us the slope of the orange line. And then we're going to do this thing where we say, what if I shrink that h value down to 0? And when we do that, it becomes the purple tangent line. So orange is secant, that's the average rate of change. Purple there is the tangent, that is the instantaneous rate of change. So when you're doing these problems that talk about average rate of change and instantaneous rate of change, if you think about this picture, you can kind of start to put it together and go, oh, okay, that makes sense. If I'm driving and I'm making observations about how fast I'm going, if I'm shrinking the intervals of my observation down, I'm getting more accurate with my observations, right? It makes sense. So that's a pretty important key to understand when you're doing the actual rate of change problems. Okay? If there's any questions about that, feel free to ask, because that's kind of a big topic. It's kind of a big thing it's pivotal. So make sure you kind of can make sense of that. Okay. So what was the next thing I wanted to do? Okay, then we're actually going to get into some of these. Okay, so let's go back and actually look at some limit problems. And we may even, I think I'm going to show the book a little bit. I think I closed that window. Yep, looks like I closed it. So let me open it here. So limits is kind of, we've got introduction to limits here. It's like a lot of stuff. That's like a major topic to put into one section. In fact, most books cover limits over like half a chapter. They don't try to put it all into one section, but it's kind of important. Again, watch the videos that are in Canvas because they're pretty important. So let's open the text here, actually. Let's go teacher preview, and then let's look in the ebook because I want to show you some things. These are pretty important. So I'm not just going to, as you can see, I haven't even opened this till an hour in, but I don't love just teaching out of the book. But a calculus book has really good drawings that if you can understand the drawings in the book, all of a sudden it starts to go from being memorizing some problems on your homework to, oh, I actually get what we're talking about. And then really that's in some ways one of the things that separates, people in those careers is the ones that can actually do the math, or the ones that, can become quants on Wall Street and stuff like that are doing the, making big bucks and stuff like that. Okay, so let's blow this up a little. So this picture here gives us the concept of a limit, and we have sort of the intuitive idea of a limit, what a limit is, and then we have what we have to do to actually calculate limits. And none of it is necessarily easy. There are some people that just sort of intuitively get limits, like right from the beginning. They're just like, yeah, I get it. And then some people really struggle with it. So don't beat yourself up. I think a lot of it has to do with some people are just better with like understanding how things are, spatially oriented things, and those people sometimes get limits a little faster. Some people struggle with spatial orientation, and limits are just a little bit more challenging from them. And at first, when I explain the limit, you might go, well, that doesn't even seem helpful. Why do we care about that? But as we'll see, part of the reason you won't think it's that helpful is because you to this point have not really dealt with very complicated functions. But that's the point of calculus, is to deal with very complicated functions. So as we get into more complicated functions, you'll start to go, oh, okay, I kind of see how we need the limit to describe that. Okay, so this picture is helpful. We talk about the limit as x approaches a certain value, oftentimes c. So what we're saying is on the x-axis, we have some value c, and that c corresponds to a function value. So if you take your function and you find the function value with this value c, what is the output? Now that right there should seem kind of familiar, and you go, well, that doesn't seem like a big deal because that's just finding a function value. We've done that in algebra. That's nothing new. And that's right, for the kind of functions you've dealt with, that was always easy to do. But what if you're concerned about what's happening around C, but your function is not defined here? All of a sudden, it gets a little bit more complicated, right? So for instance, let me show you. I've got one ready here. This one. This just looks like a straight line, right? But that's a little deceiving. It's actually this function over here. Let's see if I can shift this. X squared minus x minus 12 over x minus 4. That's actually what the graph is. So when you saw the line, you were probably expecting something like y equals 2x plus 3 or something like that, right? Well, that's not what we've got over here. We've got actually a rational function. So what that means is What if I wanted to know about the function value at 4? Well, we could look and go, well, it looks like at 4, the value is 7. Except be careful, this function's not defined at x equals 4, right? Because if you plug x equals 4 into this expression right here, you get a 0 in the denominator. You are not allowed to have a 0 in the denominator because it's nonsensical mathematically. It doesn't make sense. It's dividing by 0. And if you just think about dividing by 0, it's silly, right? How many zeros does it take to add up to 6? It doesn't make sense to ask that question, right? So in this case, this is not actually a line. This is a line that has a little hole in it right here. Right at x equals 4, there's a hole there. Now, you may have learned this somewhere along the way in your K-12 career or in college or whatever. You may have learned to put a little hole on the graph when that happens, which is great. That's really helpful. The problem with that is modern graphing software doesn't do that, right? So it's almost like we teach students to do something that modern graphing tools don't do. So it's confusing. So like Desmos and, some of you might be using computer software depending on what areas of business you go into. They're usually not going to naturally put a hole there. So you just have to know there's a hole here, right? So this is not really a line. It's a line with a hole. But what if you wanted to know what was happening right around that hole? That's the kind of questions we ask in calculus. What's happening around this problem point? I can't evaluate the point, but can I ask what's happening around it? Yeah, that's what we do in calculus. Okay, so that's an example of a function that seems very easy to deal with, but all of a sudden when you actually get into it, it's a lot more difficult. Okay, it's a lot trickier. Okay, so let's zoom out so I can see what I wanted to talk about. Okay, so here's our notation. Limit notation. And I know one of the things that's confusing in any math class is you have all this new notation to learn and it just looks ridiculous sometimes, and it's like you're learning a new concept and at the same time you're trying to learn a new notation for it, and it all just gets very confusing. But we'll make sense of this, but do make sure you spend a little time trying to grasp notation. It will make the whole class a lot easier. So we say the limit of f of x as x approaches c is L. That's a language that you hear a lot in calculus, like that phrase. The limit of f of x as x approaches c is L, except sometimes we'll have different values in there. We'll put a number in there or an expression or something like that. But those phrases, the limit of as x approaches, you hear those regularly. The way we write that mathematically is as this. The limit as x goes to c, or x approaches c, of f of x equals L. Right? You'll hear people say goes to and approaches interchangeably. You hear both of those a lot. Right? So the limit as x goes to c of f of x equals L. If we can get as close as we like to L with f of x by taking x sufficiently close to c. So what does that mean? We'll go back to our problem here where, let's see if I can... wonder if I can do this easily. Probably not. It's actually going to make it harder to see, I think. Well, let's see. X. There we go. So I just kind of put that hole in there that so we could kind of see where it was when we're looking at the graph. In fact, can we even make it a little smaller, I wonder? Oh, that's too small. A little better? Okay, let's try that. So let's see. As our x approaches 4, well, at x equals 4, our function's actually undefined, right? Because we have a little hole right here. But what's happening right around it? So what it's saying is if we can get x really close to 4, not equal to 4, but really, really close to 4. So think 3.999999999 or 4.000000001, right? Values that are really, really close to 4. Can we predict what the y values up here will be? So it looks like if this is if this is 4 right here, as our x's get close to 4 from below, like 3.9999999, we see the y values are getting really close to a specific value. So that's what they were talking about in this language when they say, if we can get as close as we like to L with f of x by taking x sufficiently close to c. So if this is our L right here at 7, we can get a y value as close as we want to 7 by taking an x value as close as we need to 4, right? So our x value would be really close to 4, 3.99999, and that would give us some kind of x value, 6.9999999, getting really close to 7, right? That's what they mean. That's what that line means when they say that, okay? And I know that's probably not 100% clear at the moment, but all these things will start to make more sense as you work on these limits a lot more. But like I said, this is kind of the big section in this chapter. Like, it should be a little bit daunting. So here you see like what I was talking about. Here's an example. Let's see how I can get that on screen here. Oh, we can cut that top part out. So we're interested in find the limit as x approaches 2 of the function, this rational function right here. So notice it's like what I just said, where we want to know the function value around 2, but look, if we plug 2 in, we get 0 in the denominator, and that's a big problem. Okay, so how big can I make this? There, and then we'll go up. Okay, so we have the function here, 3x squared minus 2x minus 8 over x minus 2. We're concerned about at right around 2. So there's now an advancement of our notation. Do you see how, yeah, you can see it on the screen there. See how they have x goes to 2, but then there's a minus here? And then here we have x goes to 2, and then there's a plus. That's telling you the direction that you're approaching 2. So if you see 2 with a minus superscript, that means you're approaching from the minus side, from the negative side. That's the left. And over here you have the plus. That means you're approaching from the positive side. That's the right. Okay. So just think about your number line. If you go far enough left, you get into negatives. If you go far enough right, you get into positives. So that's why they use the positive and negative symbol. It tells you from what direction are you approaching that value. Okay? So we've got some x values, and then we've got the function. So you can see, well, we know at 2, if I plug 2 in here, I get undefined. So I can't even plug in 2. But our question isn't really what happens at x equals 2. It's what happens as our x values get really close to 2. So you can see what's happening with our x values. They pick a sequence of x values, 1, 1.5, 1.7, 1.9, 1.99, 1.999, 1.9999, 1.999999. That might have been one too many nines, but you get the point, right? We're getting just infinitely close to 2, but without actually putting in 2, because we can't put 2 into this function. But look what happens to our y values when we plug these x values in. At first, we get 7, then 8.5, then 9.1, then 9.7, 9.97. Do you see how they're approaching a specific value? What are they getting closer and closer to? Well, it looks like as our x values are getting closer to 2, our y values are getting closer to 10. Okay? So we would say the limit from the left as x approaches 2 of this function is 10, right? What are our y values approaching? Notice if we approach from the positive side, we get the same thing. So you start at 3, 2.5, 2.3, 2.1. Notice these are getting closer to 2, but we're never putting in 2 because we can't. But we're getting as close as we want to 2. We could do 2 point and then like 100 zeros and then a 1. right? Really, really close to 2, but not quite hitting it. And look what our y values are going to again. Oh, it looks like they're getting close to the number 10, right? So what that means is, over here on our picture, to use the language of limits, as our x values approach 2, our y values approach 10. That's what we're saying when we talk about a limit. The limit as x goes to 2 of this function is 10. Okay? Now, you sometimes will talk about one-sided limits. The limit exists if the two one-sided limits exist and agree, and these are the two one-sided limits where you approach from the left and you approach from the right. See how they're going to the same number, 10? Then the limit exists. You're going to have questions that say, does the limit exist? In this case, yeah. Oh, okay. Okay. So that's important. You sometimes will have problems where on the left side, your numbers are approaching, say, 5, and on the right side, your numbers are approaching 7. Well, then the limit does not exist because you're approaching different values from the different sides. The one-sided limits exist, but the full limit doesn't exist because they're going different directions, right? That would be, I show you an example of that in the video that I have in Canvas. I think, or is that the continuity? Anyways, I believe I go over some examples like that. Okay. And if there's any questions on this, feel free to speak up. Oh, here's a good example. So here we have a piecewise function. Hopefully you remember how piecewise function. Oh, where are you plugging in those numbers to get it close to 10? Oh, okay, great question. So if you didn't see, we're plugging them into this expression, 3x squared minus 2x minus 8 over x minus 2. They're taking these x values and they're plugging them into this. So anytime you do a limit, there will be a function in that problem. In this case, it's this one, the 3x squared minus 2x minus 8 over x minus 2. They always have to specify a function. Now, that function could be in the form of a picture, like a graph, like this, or it could be in the form of an expression like this, but they have to give you a function in order to figure out where your y values are going. Okay, so it's that. So you'll always be taking the limit of some specific function, so you plug your x's into that function. Yeah, good question. Okay, this is a piecewise function. This happens a lot. You'll see this a lot in business, actually. Students struggle with piecewise functions, but you definitely see them in like business settings because, like prices, let's say that your price is based on a certain thing. Well, you could say, well, if you buy less than 10,000 units, then we give you this price per unit. If it's above 10,000 units, then we give you this other price per unit. So what you have is a series of different rules depending on how much of something someone's buying. Because in general, in business, if you buy more of something, you get a better price, right? So you have different rules depending on how much someone's buying. So that's what a piecewise function is we give you, instead of just giving you one function to evaluate, we give you 2 or more. You could have 5 rules up here. But over here on the right tells you when to evaluate those. So basically for this function p of x, let's say that you care about a function value of where x is 50. Then you go over here and say, where does 50 fall? Is 50 between 0 and 150, or is it between 150 to 350? Well, 50 is in this first one. It goes here. So that means you're using the top row for your function. Okay, so for that particular moment, you can ignore the second line and just work with the top one. Then let's say the person that you're dealing with says, oh, that's not a very good price. I don't want to buy 50 units. I want to buy 300 units. Does that make a difference? Then you'd go, yeah, okay. So an x of 300 now falls in this interval down here, which means I can ignore the top line and just use this one down here. So then you would use this for evaluating your function. Okay. And piecewise functions often end up like this, where you have like different segments that don't join up. See how we have this? This is called a discontinuity, and it's actually called a jump discontinuity. It's not a hole like when we looked here. This is called a hole discontinuity because they're close. It's just one point got poked out. this, where did it go? This is called a jump discontinuity because you kind of can imagine why. You'd have to jump in order to get up to this piece right up here, or you'd have to jump down. You can't just, by just putting one hole in there or putting one more point in there, you can't make these line up. So it's a jump discontinuity. So they look jagged like this. So you could notice if you wanted to talk about limits, see in this case they say the limit as x goes to 150 of p of x does not exist. Well, let's look at the two one-sided limits. Actually, they don't look at the one-sided limits in this example. That's right. But let's say we cared right at 150. Well, if you're coming from the left, your y values are going to 2900. But if you're coming from the right, your y values are going to 2750. So the two one-sided limits exist, but they don't agree with each other. Therefore, we would say the limit as x goes to 150 does not exist. Okay, that doesn't exist there. And again, you can look at your kind of this reasoning that I just gave. You can see it's now in table form. So you're taking your x's, and like the question a minute ago, well, where do the function values come from? You use the function that's given in the problem, this one up here. So you'd take these x values here, you'd plug them into this function, and you get your corresponding y values. Okay, and we can see as x is approaching 150, our y values are approaching 2900. We can also see that in the picture. As x is getting closer to 150 from below, the y values are getting closer to 2900. Okay. Likewise, as our x values are getting close to 150 from above, so from the higher values, our y values, you can see, are getting closer to 2750. We see that in the graph right here. Right, they're getting closer to the 2750. So they don't, the two one-sided limits don't match up. So here's a theorem. If the limit as x goes to c of f of x is equal to L, if and only if the limit as x goes to c from the left of f of x is equal to limit as x goes to c from the right of f of x is equal to a limit L. So in other words, that's what I've already kind of been saying a few times. The two one-sided limits have to exist, and they have to agree with each other. Okay. So if you're doing a problem where they say, does this limit exist? That's what you're going to do. You're going to look at the limits from both sides, see if they exist, and if they exist, do they agree with each other? If the answer is no, then the limit does not exist. If the answer is yes, then it does exist. Okay. And we've got some basic properties using limits. Let's see, I want to get to a little bit more complicated stuff. This stuff I think you can get from watching the videos in Canvas. I think you'll be able to make that work. Yeah, those are all pretty good. Yeah, and there's good examples in the book, so make sure you're kind of watching that. Okay, now we get into... So the language that we use to describe limits can be confusing because sometimes we'll say something doesn't exist and then we'll say it's infinity. And it's easy to go like, well, which is it? Does it not exist or is it infinity? And the answer is both, which I know is confusing. But do you see how... See, I can do a better version of this. Let's do I know that's not right. Let's see. What was it? It was x squared minus x minus 3 over x plus 1. Okay. Do you see here how right at x, so I'm putting in our vertical asymptote. If you remember that from your algebra class, the vertical asymptote is where these curves come in and they approach that purple line, but they never quite touch it. right, on both sides, and this one's coming up and not touching it. But it looks like they touch it in the graph, but mathematically they never quite get there, right? So what we would say in this case is that the limit from the left, see how our y values are shooting up towards infinity? We would say the limit as x goes to -1 of this function from the left is infinity. But look on the right side. If we approach from the right, our values are shooting down towards -infinity. So the limit as we approach, as x approaches -1 from the left is infinity. The limit as x approaches from the right to -1 is -infinity. Those numbers don't agree. They're technically not even numbers, but they don't agree. So the limit does not exist. But also, when we say that the limit is going to infinity, it still doesn't exist because infinity is not a number. The limit has to be a number L, but sometimes we will write the limit equals infinity because that tells us not only that it doesn't exist, but it tells us which direction it's going. Both of these one-sided limits don't exist, but this one's going to infinity and this one's going to -infinity. So saying the left-sided limit goes to infinity is more informative than just saying it doesn't exist. Does that make sense? It's a way of giving a better answer with like more details in it. But sometimes people get confused because they say, no, it exists, it's going to infinity. And that counts as not existing, right? And again, I know, like, I'm trying to fill in the details. Like, I don't expect you to finish today's lecture and go, oh, I totally understand everything he said. But what I'm hoping is that when you watch the videos later, the things that I've told you in class, you'll go, oh, that's what he was talking about. And it'll start to all kind of get pieced together. But this class today is not enough to like really help you understand limits all by itself. You want to make sure you watch those videos. Yeah, here's an example of like where we did one like this in class where there's a hole punched in the graph. Yeah, so there's good examples in here. And then we have limits involving infinity. So this throws students for a loop too, because infinity can come up in two ways. Like this one here that we just looked at or talked about. Here, the y values were going to infinity, right? The x values weren't going to infinity. Here the x values are going to -1 and the y values are going to infinity. But when we talk about limits at involving infinity, notice how here they're talking about the x values going to infinity. So you want to make sure when you're dealing with a problem where we talk about limits and infinity that you're specifying, am I dealing with a problem where the y values go to infinity or where the x values go to infinity? Because it's very different. They are very different things, and you're going to get confused if you can't tell the difference. Okay, so this says the limit as x goes to infinity of c of x. Okay, and actually we'll talk about cost function here in a second. This is important. You'll all sort of need to know how to do this, and there's it's not a good sign. When I teach this class, there's usually a couple people that get to the end of the class and they don't understand cost functions, revenue functions, and profit functions, and hopefully it doesn't take much explaining to have you realize that if you're going into business or economics or something related to that, you need to know cost, revenue, and profit functions. But anyway, so this, we're going to do that in a second. This is the limit as x goes to infinity. So here x is going to infinity. We're sending x down the x-axis just forever. It's like it's on the speed trains or whatever, what do they call them? The really fast trains. You're just zooming down the x-axis like super fast, right? You're passing 1 million, you're passing 1 billion, you're past 1 trillion, you're just zooming down that x-axis. What are the y values doing? So that's the difference. The one we did a minute ago, the y values were going to infinity. The problem we're looking at now, the x values are going to infinity. So what's happening is, see how the y values are leveling off right around 200? So the y values are going to get closer and closer and closer to 200, but never quite touch it. So the limit of this function as x goes to infinity is 200 because that's where the Y values are going. The limit is always just asking what's happening to the Y values when we do this to our X values, right? It's like a simpler way of stating it. This tells you what your X values are doing. And then you just want to know, like, well, what are the Y values doing when I do this? What happens to them? Okay. Okay. I have a video on this in the Canvas page, but it's super important. One, because it comes up again and again and again in these problems that you're going to be working on throughout the whole semester. But also, again, it's sort of a fundamental thing you need to know if you're going to be in a business type major. So that's cost, revenue, and profit. Profit's pretty basic. The profit is just your revenue minus your cost, right? That one's usually pretty easy. So revenue is how much money you're bringing in, and cost is how much money you're sending out, right? How much did you pay is your cost, and revenue, and revenue is how much you're bringing in. So revenue. So, like sometimes you'll do problems and they'll give you a revenue function. They'll just say, here's R of X. That's our revenue function. And they give you a polynomial or a rational expression, and that's fine. Then you keep working. Sometimes what they'll do is give you information and you have to figure out what the revenue function is. So for instance, they might say, find the revenue function for a company where our price is this. Find the revenue function. Well, if you think about it, revenue, that's the amount of money you're bringing in. Well, how much money do you bring in? Well, it's the price of the product that you're selling times the number of units that you've sold, right? If you have a lemonade stand and you're selling lemonade for $2 a glass and you sell 100 glasses, well, then what's your revenue? It's $200. How did you get that? You multiplied the number of glasses sold times the price of a glass of lemonade. $200. So that's how you calculate revenue. Now, sometimes your cost will be a fixed rate, like $2 for each glass of lemonade. But like I mentioned, sometimes your price is actually a function. Like I mentioned, where, in the real world, the more you buy of a product, usually the better price you get. So a company may say, well, tell us how many units you're going to buy and we'll tell you the price, right? So just keep that in mind. Your revenue is your price times the number of units sold. And usually when we do these kinds of problems, this X, that's the number of units sold, right? So if you have a price P and you've sold X units, then your revenue is X times P, right? You'll get some practice with this, but you want to know those basic fundamentals. If you can think through that, which, someone who's taking this class should be able to sort of piece those things together, that it'll start to make sense to you, okay? Cost works a little bit different. Cost is usually composed of two pieces. You have a fixed cost and you have a variable cost, okay? That's almost always true in any kind of a business. So your fixed costs are things that don't change. So this might be the insurance policy that your company uses. This might be the lease agreement that you have, right? Let's say you have a business down in the industrial portion of Ventura. You rent out one of those buildings in that industrial zone and you build bicycles in it, okay? Well, the person who's renting you that spot doesn't really care how many bicycles you sell, right? They're just like, here's what I want for rent every month. Pay me. And it doesn't matter if you make 0 bicycles or 1,000,000 bicycles. They just want to know, just pay the rent, right? That cost does not change based on how many units you sell. Your insurance policy probably does not change based on how many units you sell. There's lots of things. Maybe you have to buy equipment, not equipment for the bikes, but tools or equipment that you need to build the bike. So you don't have to buy that tool every single bike you make, but you might need it at the beginning of your company. You might need to buy $10,000 worth of machinery in order to make these bikes, right? So those are fixed costs. The variable costs are the pieces that change based on how many units you sell. So if I'm just going to make one bike this month, then I only need the parts for one bike, right? Maybe I have to buy $200 worth of parts to make one bike. Well, then my cost for making the variable cost for that bike is $200. But if I'm going to make 10 bikes, then I need 200 times $10 to buy the materials for the bike, right? That varies depending on how many bikes I'm going to make. So your cost function is your fixed cost plus your variable cost. So again, sometimes in these problems, they will just say, here's your cost function, and you can actually look at it and you can go, oh, that's the fixed part because there's no variable in it. You go, that's the variable part because there is a variable in it. So you can kind of see the different parts of the cost. Sometimes they will just tell you, right? They'll give you the pieces of information. Each bike that you create costs $200, and you have lease and insurance policies that add up to $2,500 a month. Create the cost function. We have to figure out, okay, so what does it cost me each month for the fixed part? And then, you get those clues from the problem. And then you go, okay, well, then how much is it going to make me for each bike? And then you multiply that times X, and you have the variable part. You put those two pieces together, and you have your cost function. So there's a video on that in Canvas, but it's pretty important that you kind of get that together. And here they're already jumping into average cost. So that's interesting because sometimes you just want to know the average cost of what you paid, because we're going to get into some complicated topics where we talk about like, well, you just bought a load of bikes, but the 10th bike cost you this much and the 10,000th bike cost you this much. But at the end of the day, you don't really care, right? You just want to, it's not like you're going to sell the different bikes at different prices. You're going to sell them all for the same price, right? So sometimes you just want to know the average cost. And this one kind of can throw people a little bit. If you want to, here they just give it to you. They tell you, let's suppose the average cost is this. But in general, when you have a function and you want to figure out the average, you just divide the whole thing by x, which makes sense. What do you do? What would you do if you wanted to find the average test score? Well, you would add up all the tests, and then you would divide by the number of tests, right? Well, in these problems, the number that you're dividing by is x. That's the number of units sold. So that's why a lot of times in these average costs, you'll see something being divided by x. That's why, because that's literally what the average is. You divide by the number of things, right? You add up the test scores, divide by the number of tests that there were, right? So that's why you're dividing by x in those. So just kind of pay attention to that. Usually the bar above it, that means you're dealing with an average. So if you're doing a problem with a capital C of x, that's probably your cost function. If it's a capital C of x with a bar, that means average cost function. So pay attention to that. Let's see. Okay. We still have some time left. Let's see what we want to cover here. Oh, okay. So this is an explanation as to, let's pull up this. There's a couple things that can happen when we talk about, you probably in algebra called this end behavior. It's what happens to your functions when you go down the x-axis in either direction towards infinity. So look at this part of the function. As x goes to negative infinity, see how our y values are shooting down towards negative infinity? So we would say the limit as x goes to negative infinity is negative infinity, right? What are the y values doing when the x values go to negative infinity? They're going to negative infinity. Yeah, and Kyle, the comment that was made in chat, it's making me think of determining outcomes of domain and specific range constraints. Sort of. It's usually a little bit more about making little domain constraints and figuring out what that does to your range. But yeah, that's the right idea. I think you're basically thinking about it the right way. Okay, so we can see that one outcome is that our functions can shoot down towards negative infinity on one end, right? And on the other end, we're shooting up towards positive infinity, right? So we can see that a function can shoot up towards positive infinity on one end. And then we saw here in the graph, I'll just show you one. There's another thing that can happen. Here, our functions can level off at a specific value. In this case, they're leveling off at 0. So on the ends of your graphs, usually we can go up to infinity, we can go down to negative infinity, or we can level off at a certain value, right? That's usually what occurs. Well, for rational functions like we've been looking at here, there's an easy way to tell, and it's called this dominant term property, which basically means think about how a fraction works. Take a fraction, just like think about this not even in terms of polynomials. Just think about fractions for a minute. Take a fraction, like say 1 over 1, right? Now make the denominator bigger. So the numerator is staying at 1, but the denominator is becoming 1, 10, 100, 1,000, 1,000,000. What's happening to that fraction? Well, as the denominator blows up, the whole fraction is shrinking. So as the denominator grows, the fraction shrinks. All right, what about the other way around? Think about our fraction being 1 over 1. Now the numerator is growing and the denominator is staying the same. So the denominator stays 1, but the numerator is becoming 1, 10, 100, 1,000, 1,000,000. That number is getting bigger. So when the numerator blows up, the fraction blows up. When the denominator blows up, the fraction shrinks towards 0. So that's the kind of thinking you want to be able to do with fractions in general. And if you can do that, then this dominant term property becomes a lot easier to do. Because take, for example, this example they give us. We want to know the limit as x goes to infinity of 8x cubed plus 7x minus 2 over 5x squared plus 3x plus 11. Okay, so let's think about that. We'll look at the graph of it in a minute, but without even looking at the graph, let's see if we can think about what would happen as x goes to infinity. Well, think about these terms in front, x cubed and x squared. If we're putting in really, really big numbers, think bigger than 1 trillion, think a number that is 100 digits long, right? We're talking about big numbers, numbers that are millions of digits long, really, really big numbers. Well, if I take a number that's 100 digits long and I plug it in here for x cubed, is this minus 2 really going to make much difference? Or even the 7x? The answer is no. When we're sending x to infinity, the only term in the polynomial that really matters is the one with the biggest degree, because it's going to be so much bigger than the rest of them that it is in total control of what happens, right? When we plug a 1,000 digit number in here for x and cube it and multiply by 8, this minus 2 is insignificant, and we can basically ignore it, right? Think of this x cubed as the bully. It gets to bully the rest of the polynomial. Okay, so in this problem, the only terms that really matter are these ones in front. And this is sometimes, here they call it the dominant term property, but it's usually called the lead coefficient test, where when we're looking at end behavior, we only have to worry about these terms in front. So what's going to happen when I take a 1,000 digit number and I put it in here for x, I cube it and multiply by 8, and then on the bottom I square it and multiply by 5? Well, even then, this x cubed term is going to completely dominate this x squared term. It doesn't matter what this x squared term is doing. This x cubed term will be so much more in control that all that really matters is that one. So what this means is we're in that case of a fraction where we have the numerator blowing up. In this case, they're both blowing up, right? If we send x to infinity, the numerator is getting bigger and the denominator is getting bigger. But the numerator is getting bigger in a way that makes the denominator feel silly, right? It's like having a rabbit race a tortoise, right? I mean, and it's not like the story where the rabbit falls asleep, but like assuming the rabbit just keeps running, right? The rabbit's going to be miles ahead of the tortoise. It doesn't matter that the tortoise is creeping ahead. If the rabbit doesn't stop, it controls the entire race. Right? So that's what's happening here. The numerator and denominator are blowing up, but the numerator is blowing up so much faster that we can say, okay, big numerator in a fraction means the number's getting bigger. This thing must be exploding to infinity, right? And we can see down here that it in fact is. the limit as x goes to infinity of this, you can see basically they're writing in math what I just explained to you. See how they're ignoring these 4 terms right here? They don't even write them in the second step because the lead terms are the ones that matter, the ones with the biggest exponents. And then we say, okay, well, what about when we cancel the x squared out? Well, it looks like the numerator is going to blow up faster towards infinity. Okay? So that's one way. You can look at those. You can just show someone a rational function and say, what happens with this go to infinity? And in a fraction of a second, they'll say, oh, the limit's infinity. And you go, how did you know that? And it's because they just sort of understand how a fraction grows or shrinks. And they can go, oh, well, I know where the lead term is, and go from there. Let's look at this one. Notice that so in this one, the largest degree term is in the denominator. So that means our denominator is going to be blowing up faster than our numerator. So if the denominator is growing, that means the whole fraction should shrink down towards 0, like our function of 1 over x that do I still have it up here? Yeah, right here. This is our function 1 over x, and look what's happening to our y values. They're approaching 0, aren't they? Because the denominator is higher degree than the numerator. So they're approaching 0. So that's, you can see here, our limit is that it's going to 0. So they're mathematically sort of justifying what I just said conceptually. And that's why, I mean, you can forget the mathematical steps sometimes, but if you understand conceptually, it'll help you rework your way through the mathematics of it. So this limit that we started with, we can ignore these insignificant terms on the bottom. We look at this, we cancel out the x, and go, well, this thing in the limit, we can pull the 7/2 out front. That's a thing you'll see in the videos in Canvas. We can pull the constant out front. The limit is 1 over x goes to 0, so the whole thing goes to 0. And that's sort of brought up here. This is summarizing that. It's basically saying there's 3 cases for a rational expression when you look at the limit as x goes to infinity. If the degree of the numerator is less than the degree of the denominator, the whole thing goes to 0. Again, just think of it as a simple fraction. Okay, if my denominator is getting bigger, faster, then the whole fraction shrinks towards 0. Okay, that makes sense. Degree 2, oh, we haven't talked about degree 2 yet. Let's do degree 3. We looked at that one. If the degree of the numerator is greater than the degree of the denominator, then the numerator is blowing up and it's going to go up towards infinity, like the example we saw a minute ago. Degree 2 we haven't talked about. Let's look at an example of that. Let's clean things up a bit. Okay, so I just made these things up, but we're looking at the end behavior of these. We want to know what's happening as x goes to infinity. Well, it looks like they're leveling off, but at what value are they leveling off at? Well, if we look at it, is that on screen? Yeah. Okay, so the degree of the numerator is equal to the degree of the denominator. In other words, the numerator and denominator are blowing up at the same rate. So they basically cancel each other out. These other 4 terms we don't even care about. Those are just junk terms. We can ignore them for this particular question, right? When we talk about end behavior, those terms don't matter. The x squareds are going to cancel, and what we're going to be left with is 3 over 2. So that horizontal asymptote should be y equals 3 over 2. And it looks like it is. Looks like they're leveling off right at that blue line, right? So a couple things. One, I want to show you that's what they mean right here. When the degree of the numerator is equal to the degree of the denominator, then the limit as x goes to infinity is the ratio of the coefficients of the dominant terms. That's where I got 3 over 2. It's my coefficients on the x squared terms. Okay. Another thing I want to show you is sometimes we get a little lazy with our wording and we say things like, a graph can never cross an asymptote. Well, you're looking at it right now, cross an asymptote. A graph can never cross a vertical asymptote. It has to make a jump, but it can cross a horizontal asymptote. In the end behavior, way out on the ends, it won't touch it. But in the middle of your graph, you can cross it. So what's actually happening here is the function drops down below the line, and then it starts going back up and approaching the line from below. So sometimes, like with 1 over x, you see the curve just comes down and approaches the asymptote. But sometimes you'll get this where it drops below and then starts to come back up. Okay, so do be aware, you can cross a horizontal asymptote in the middle of the graph, but you won't do it on the ends of the graph. Okay, that's just one where sometimes people are kind of lazy about how they say that, how they phrase it, and then it's actually incorrect, and it can be a little misleading for people. Okay. Right, you've got your horizontal asymptotes, your vertical asymptotes. Those are the lines that your function is approaching, but never quite touching. Horizontal means kind of level, like you would, like a road. If you're walking on a road, it's horizontal. If you're climbing up the side of a building, that's vertical. And you see lots of places where limits occur, right? Like they give an example here. Like they're starting off here. Someone who's 200 pounds starts to lose weight. They'll lose weight very quickly. But as their body has less and less fat to burn, they'll lose weight slower and slower because their body's having a harder time accessing what little fat is left. So what'll happen is you'll see this kind of behavior where it gets closer and closer to 200, and you're just sort of getting closer, but you're not seeing that same ability to lose weight as when the person was 200. You'll see this too in all sorts of settings. Say you have temperatures. Say you take something that's really hot, like you take a hot pot. You know, maybe you're making some spaghetti, and you take the pot off the stove, and it's really hot, and you set it on your tile, which is just room temperature. At first, that pot is really going to start cooling quickly because lots of that excess heat is being pulled out by the tile. But over time, as those temperatures approach each other, the temperature change will slow down. And so you'll see that kind of asymptotic behavior where the temperature at first is really going down because the tile's just sucking up all this heat. But then as they get closer together, the temperature does not change as quickly. Okay, so that's limits. Again, it's a huge topic. I don't expect when this class is over that you totally will be like, oh, I totally get that. In fact, if you do think you totally get it, that might actually be a little worrisome because the limits take a little time to fully grasp. You might have a pretty good understanding of what I said, but to really understand them is going to take a little while for it to sink in. Let's look at and if there's any questions, feel free to ask. Otherwise, I'm going to talk about continuity a little bit. Well, let's see if there's any problems I want to look at here before we go. Yeah, I think these should all make sense to you. And you've got the video if you need some help. Yeah, okay. Let's go back. Let's talk continuity, functions and continuity. Oh, and then there's average and instantaneous rate of change. So let's see. Let's do this real quick. So you'll see the different types of discontinuities that you can have. You'll play around with those a little bit. You'll talk about limits in terms of those. Basically, the loose intuitive definition of continuity is can you draw it without lifting your pencil off the paper? Now, that's not a technical, rigorous definition, but it's how you can think of it. Could you draw this graph without lifting your paper off the pencil? Or I guess most people would lift their pencil off the paper. Could you draw it that way? No, You can't do that because there's this gap right here, right? So this would have a discontinuity. This part, this parabolic piece, that at least this section of it is continuous because I could draw that without lifting my pencil, but I can't draw the whole thing without lifting my pencil, right? The rigorous mathematical definition involves limits. That is, if at any given point the limit as x approaches that point is equal to the function value, then you're continuous, right? And you might think, well, why don't we just use that intuitive definition? And the answer is, if you go into, like, especially in the engineering calc, and you become a, like engineering students and math students, you end up running into functions that are very, very bizarre, and they kind of don't work if you think about it as lifting your pencil off the paper, but they do work if you use this calculus definition, which is if the limit is equal to the function value, then it's continuous. Then it makes sense. That's why we do that. It's not just because we want to make things complicated. It's because you actually need it sometimes. Like, this thing is continuous. It's kind of weird looking, but it's continuous, right? You could draw this without lifting your pencil. Okay, I think people can get through that. Should be fine. I want to talk with a little bit of time left about 1.6. Where did it go? So that's average rate of change and instantaneous rate of change. So whenever someone says average rate of change, you should immediately think secant lines. Those can be done with algebra. Whenever someone talks about instantaneous rate of change, that involves calculus. Okay, so it's back to that picture that I had. The orange one, that's a secant line. That represents average rate of change. You find 2 points, and you find the slope of the line that goes through them. That's, you did problems like that in Algebra 1. Here's 2 points. Find the slope of the line that goes through them. That's your average rate of change. Now, the tangent line's a little trickier to find as you shrink this x towards 0. So basically what you do is you take the secant lines and you take the limit as h goes to 0, and it becomes the tangent line. So let's look at some examples on here. So they say for this function, so first they have you calculating some difference quotients. Remember, that's how we started off class today, was with some difference quotients. So you'll do that. They don't actually use the term difference quotient here, but they give you a function. They give you a difference quotient. It's not unusual to have on tests for there to be a quadratic used in a difference quotient. So be able to do a quadratic. Like, lines are pretty straightforward. They're pretty easy. Quadratics take a little bit more work, like the one we did in class. You should be able to do those by the time the test rolls around. So there's a bunch of those. Okay, for this function, find the average rate of change for the function on this interval. So you're given a function. Let me blow this up a little. Okay, you're given a function over here, and then they want to find the average rate of change on this interval. Well, this interval goes from one x value to another x value. Those two x values give you the point that you care about. So you take the first x value, you plug it in here, and you figure out the y value. That's your first point. Then you take your second x value, you plug it in here, figure out the y value. That's your second point. Now you have 2 points. You can find the slope between them. So let's take a look with one where the numbers come out a little nice. So find the average rate of change of f of x with respect to x on this interval. So our function is x squared plus 3 from -3 to 2. So I wonder if I can just get a view. That's kind of small. Let's see. Let me just get it so there's some work here I can show you. Okay, so let's move him back just a bit, because I don't have enough time to work through a full problem. But you can see what he's done here is he's taken the problem that he's given in here. Actually, I don't really like the way he's doing it, but Basically, he's taking an x value of 8, and he's finding the y value that corresponds to that is 13. That gives him 1 point, 8 comma 13. Then he takes the second x value of 2, plugs it into the function, gets a y value of 7. Now he has a second point, 2 comma 7. Once you have 2 points, you just throw the slope formula at it, and you have the average rate of change. Okay, so that's what he's doing in that problem. Same thing here. You've got a polynomial. You would plug 0 in there and get the y value. That's your first point. Plug 2 in here, get the y value. That's your second point. And then use the slope formula. Then we get to, where's the next one? Oh, just be aware, the algebra gets a little... It's a little bit of a step up for this one, finding the difference quotient of a rational function. You're going to have to like find common denominators and go through all that kind of stuff. Okay, look here. We talk about find the instantaneous rate of change of the function at a specified value. Let's look in the ebook. See what we can get here. So the average rate of change, this should look familiar right here, right? If I move this over. Does this formula look familiar? y2 minus y1 over x2 minus x1. Your average rate of change is literally just your slope between 2 points. So you use the function to figure out what your 2 points are, use the slope formula, and you got it. This looks confusing, but again, in calculus, we use function values to represent the y values. So this just means this, but with function notation. They mean the same thing. Yep, and here they formally give you the difference quotient. Remember how I told you before the difference quotient is just a fancy way of writing the slope? Well, if the slope is the average rate of change, then the difference quotient is the average rate of change. And remember this, sort of put this together because we're about to sort of connect these dots. Remember what we did here. We used, oops, I've got everything moved now. We used the secant lines, and we shrunk h down towards 0, and it became the tangent line. Like, remember this when we're connecting the dots in a second. The secant line, as h goes to 0, becomes the tangent line. The tangent line represents the instantaneous rate of change. The slope right here, right around that dot, that matches the curve perfectly, right? So it makes sense that that slope is the instantaneous rate of change. So when we go, where are we? Instantaneous rate of change is the limit as h goes to 0 of our difference quotient. Why? Because the difference quotient, remember, is our slope of our secant line. It's our average rate of change. And as I showed you in that picture, if we take our secant line and we shrink h to 0, remember, it becomes the tangent line? Well, that's what we're saying right here. If I take my secant lines and I shrink this h down to 0 by taking the limit as h goes to 0, then my secant line becomes the tangent line, and that slope is your instantaneous rate of change, right? Back to our example where if you're driving and you're taking at different time periods distance that you've traveled, as you shrink that time interval down, your average rate of speed, your average speed will approach your instantaneous speed, right? At 1 minute, your average speed over 1 minute is probably pretty close to your speed at any given instant. But once your speed is once that time interval is 100th of a second, your average speed is your instantaneous speed, right? So we're shrinking that h down to 0. And so that's, again, you see limits coming into play. The limit as h goes to 0 of the slope of the secant line is your instantaneous rate of change. So there's some good examples in the book. I'm out of time, so we can't go over it, but there's good videos in Canvas, and there's great examples in the book. And of course, as always, there's videos right here in the problem. So you can watch the video and watch either Octavio, Molly, or Octavio in Spanish doing that problem. Okay, they'll walk you through all of them, but that's the concept of what that problem is. Okay, any other questions? Okay, so I'm going to close down the YouTube stream. If anyone wants to talk to me, jump into the Zoom meeting, and I will... Oh, that's you're good, Kyle. Anyone who wants to talk to me, just hop into Zoom, and I'll wait as long as people are answering me questions or asking me questions. I'll help you out, and then otherwise, you're free to go. Make sure by Monday that you have that homework due, and hopefully by then you're already starting the next chapter. That's gonna be that's gonna help you. Okay. All right, everybody. Have a good weekend. We'll see you later.